This is future value, present value. Okay, actually, let's do this problem. Suppose I switch this is V. Now, you want to calculate A. I'm going to give you $1,000 10 years from today. How much is that worth to you today? So, you would just go ahead and calculate this. B is 1,000. 1.05 raised to the 10th power. And take that expression, divided by 1,000, what equals?
I got 613
Okay, that makes sense. So 613, and how many cents?
91.
91. Now, I know it's got to be something less than 1,000. Because see, you're not getting the money for 10 years. If you had the money right now, you could invest it and the money would grow to a substantially greater amount in 10 years. In fact, how can you relate these two problems to each other? How much money, if I had this much money right now, how much would it be worth in 10 years? $1,000. That's the idea of present value. So this is the future value formula right here. This is the present value formula in a discrete model where the growth process is discrete, where the growth occurs, Tyler, every year at an instant in time. Now the continuous model, yes?
I asked if we were going to relate this to real interest rates adjusted for inflation.
Okay, the idea of real interest rates, right, is you would adjust the nominal interest rates for inflation. So the nominal interest rates minus inflation would be the real interest rate, because the value of money might itself be changing. But let's ignore that. In macro, you'll talk about that.
Okay.
Let's ignore that for now. Now, what would the corresponding formulas be for a continuous model? In the continuous model, we're assuming that your money is growing continuously. And in that case, we let little r be the continuously compounded interest rate. So we switch. If we see I, that means annual compounding. If we see R, that means continuous compounding. So what would the future value formula for money be in the continuous model? We already mentioned this. Anybody remember? What's the formula for V if your money is growing continuously at R% per year? Yes.
A times E to the RT.
Yes. The future value of money with continuous compounding is given by this formula. A times E to the RT. Little r is the growth rate. Continuously compounded interest rate, if you will. So that's the continuous model. Now, who can tell me what the formula for A would be in this model if you have continuous growth? What's the formula for the present value?
V divided by E to the RT.
Yep. It's just, if you solve this formula for A, you get A equals V divided by E to the RT. Or usually, it is written usually this way, V
Minus.
times E to the minus RT. So this is the formula for present value. This is the formula for future value. So you should be familiar with these models, all four of these. This is the discrete models of growth. Future value, present value. Continuous growth, future value, present value. let me just give you one problem to illustrate this one here. Suppose you were promised, say $100,000. But unfortunately, you're not going to get that $100,000 until 20 years from today. What would its value be in today's dollars? First, I have to tell you what R is. Let me tell you what the interest rate is. Suppose the interest rate is 0.06. It continuously compounded interest rate is 0.06. What would the value of A be? Well, just plugging into this formula, it'd be 100,000. That's the future value. Times E to the minus 0.06 times 20. So this would be 100,000 times E raised to the what, 0.12? Is that right?
1.2.
Yeah, that would be 0.12, yes. Right. E to the minus 1.12. And,
I think it's negative 1.2.
It's 1.2.
oh, 1.2, oh, okay, that makes sense. Yeah, because 5% would be 1. So it should be 1.2. Oh, thank you very much. Minus 1.2, that makes sense. And what is its value equal to? Just get e to the minus 1.2 and multiply by 100,000. And what is this going to equal to?
30,119.
30,000? Thank you. Go ahead.
119.
Will, 30,019?
119.
119.
Or 119? Okay. To the nearest dollar?
And 46 cents.
Okay, 42 cents. Let's do it to the nearest. Okay. Now, your answer makes sense. Because see, you're only getting that 100,000, you're getting that 20 years from now. In 20 years, the money you invested could have compounded quite a bit at 6%. So your answer makes sense. You know the answer has to be something less than 100,000. If you get something greater than 100,000, you know you made a mistake. Because money received in the future is worth less than money received now. Or to turn it around, if you had $30,000, $30,119.42 right now, you could invest it, and in 20 years it would be worth $100,000. If the continuously compounded interest rate is 6%.
I don't know if you could find that interest rate. That'd be impressive.
Today, that would be pretty good. That would be more comparable to what you'd expect for a return invested in the stock market, or maybe risky bonds or something, yeah. Right. But I'm old enough to remember when interest rates were much higher than 6%. So today, they're much lower.
I remember my parents told me that they got an interest rate on their first car for like 14%, and that was fantastic at the time.
Yeah, that's right, back in the 80s.
It's down to 1.72 at my
I
local
know.
bank.
I know, it's amazing.
Can't
I
believe
never
it.
thought I'd live to see such low interest rates.
And it's basically.
I remember when my department head, David Shelton, this building is named after David Shelton. He was our department head in economics. He was also the dean. He told me that he had a mortgage on his house of 6%. And I thought I was so envious. And he had this mortgage rate, I couldn't believe it, 6%. This was back in the early 90s and the late 80s. That he had a mortgage interest rate of 6%. Now, 6% would be high. You had to pay that for your mortgage.
Except on student loans.
Oh, yes. I don't know, what is the interest rate on student loans?
I think unsubsidized,
6.8%, I think is what I'm getting.
6.8, I think
No.
some people I've heard are getting like 8.9 because they got like specific, like different loans or something.
Is that from a private bank?
Federal.
From the federal, even the federal government charges you that much.
Yeah.
Undergraduates though, when I was
Yeah,
in
right.
undergrad, it was like 3.2.
Yeah.
Yeah, it changes once you get into graduate school.
Then they know they can melt us.
These people are so
Well-
stupid, they're staying in school for so long.
Yep. I remember when I went to college, I had a national defense loan. And I don't even know if those things still exist. But anyway, the interest rate, I think, was only 3%.
That's pretty good.
Yeah, that was pretty good. Okay. And it was deferred, interest was deferred while I was going to school. I don't know if that's common anymore.
They do it if you are poor enough, they'll give you subsidized loans, where the interest is deferred. If you are not, they'll give you lots and lots of
I think
loans,
it's
like
only
half interest.
for,
Yeah.
Yeah.
undergraduate, the only one.
Well, so it's important for you to understand, you know, if you think of credit cards, I know credit cards sometimes have interest rates of like 23% or, you know, in that neighborhood, 20%.
Yep.
Boy, talk about exponential growth, and it's compounded daily, so it's pretty close to continuous growth. Your debt will really explode quickly at those kind of interest rates. I wish I could get, as a saver, I wish I could get those interest rates. Could you imagine that? Go to the bank and deposit money at 23% interest. No way. But on your debt,
I'd be kidding.
credit card debt, sometimes the interest rates are that high. It's terrible. So you have to be careful not to pay off your balances as much as possible. Because debt just grows so rapidly. Actually, that reminds me of an interesting problem that actually we should discuss. Suppose you have a problem like this.
Ooh, we should do our
Uh,
student loans.
We know the future value of money is given by this equation right here. V, the future value of money, is A, the present value times e to the RT. Let's assume R is the continuously compounded interest rate. And let's just use, say, 0.23. Suppose you have this situation. Your present debt is $1,000. And you want to know how long it will take for your present debt to double. So this V is 2,000. So if my present debt is 1,000 and I don't make any payments, let's assume, and assume there's no penalties or anything like that, how long would it take for your debt to double in value at an interest rate of 0.23? Well, here in this problem, we're solving for t. And you could just do this by trial and error. First of all, you could divide both sides by 1,000. You get 2 equals e to the 0.23t. And you want to solve for t. You could just do it by trial and error. Just plug in values of t until the left-hand and right-hand sides are the same. But actually, there's an easier way to do it. Any of you know, and this is something we haven't talked about yet. What's the easier way to solve this equation? This leads into the next subject we're going to talk about.
Take the log. Natural log of those.
Yeah. Yes, let's take the natural log of both sides. And if you take the natural log of the left-hand side, you get the natural log of 2 equals the natural log, and I'll put it in brackets, of e to the 0.23t. And this is something we're going to talk about soon. What can you do with this right-hand side?
Simplified point.
Yes. Yes. we're gonna learn, this is one of the rules of logarithms. If you have an expression like this, you can bring this 0.23t down and multiply it times the log of e. And what is the natural log of e? Any of you know? What? The natural log of e is just what power you raise e to get e, and that's 1. E to the 1 is e. So this is just 1. So you get the log of 2 equals 0.23t. Divide both sides by 0.23. You get t equals log 2. Natural log of 2 divided by 0.23. Now, you all have calculators. I assume that it'll calculate the natural log. What is the natural log of 2 from your calculators? Brianna?
0.69.
Okay, 0.6931. Look, that's close enough. We could go out further, but that's enough. Let's divide that by 0.23. And what do you get?
3.01.
3.01. In other words, it only takes just 3 years, basically, for the value of your debt to double. Okay, so that kind of is a warning to you. If you have a credit card debt of 20, with an interest rate of 23%, your debt is going to grow very rapidly. It's going to double in value in 3 years. Okay. So the best thing to do, if you have a credit card, if at all possible, is pay it off every month. See, if you pay it off every month, then you don't owe them anything. So that's what you should strive to do. And 23% is a whole lot worse than 6%. Even if you had to borrow money, student loans, to pay off your credit card debt, you'd be better off. All right, that leads us right into our next subject. But actually, let me just say one more thing. If you have an expression like this, e to the f of t, and you want to take the derivative of e to the f of t, what is the derivative of this with respect to t? Did you know the general formula for this? Derivative of e to the f of t with respect to t. The derivative is, yes, Todd?
F prime of t times e to the f of t.
Yes. F prime of t, just take this exponent, f prime of t times e to the f of t. Okay, so remember that one. When you take the derivative of e raised to the f of t, where f of t is just some function time. Okay. The next thing I want to talk about is logarithms. The first thing we should go over is how to spell logarithms. L-O-G-A-R. I have to look at my notes to make sure I don't make a mistake here. M-S. Logarithms. Consider logarithms, just think of logarithms as being exponents. That's really what they are. Consider this equation right here. We know that 4 squared is equal to 16. You square 4, and you'll get 16. We could also say this. We could also say the logarithm, and let's abbreviate logarithm with just LOG. But whenever you see LOG, it's an abbreviation for logarithm. The logarithm of 16 to the base 4, and this subscript gives you the base, b. The logarithm of 16 to the base 4 is what? 2. So that's the idea. Logarithms are really exponents. And you read that as the logarithm of 16 to the base 4 is equal to 2. Believe it or not, when I was young and in school, logarithms to the base 10 were very commonly used. Not so much anymore. I remember my father at one point having just a big fat book giving you different logarithmic values to the base 10 for any number you chose. Back then, when I was really young, calculators weren't even around. People carried thick books to figure out the different logarithmic values. And as I said, logarithms to the base 10 at one point were very popular. So let me just talk about log to the base 10 for just a minute. What is the logarithm of, say, 100 to the base 10? Not 10.
2.
2. So you ask yourself this. 10 is the base. What power do you have to raise 10 to get 100? And the answer is 2. Let me give you another one. What is the logarithm of 0.1 to the base 10? Negative 1. Let me write this on the right hand side while we're doing it. Notice 10 squared is equal to 100. 10 is the base, 2 is the exponent. That's the logarithm. The thing on the right hand side is the logarithm. And notice here, 10 to the minus 1 is 0.1 and 1/10. Okay, that's the idea of logarithms. I won't go over it anymore. We could go over some more, but that's enough. One thing that is worth mentioning is logarithms can have negative values. And if they have negative values, that means, excuse me. Yeah. That means what you're taking the logarithm of is some fraction less than 1. So if you're dealing with numbers that are less than 1, the logarithmic values are going to turn out to be negative. Trick question. What is the logarithm of to the base 10 of a 0?
Error domain.
Okay, very good. Why does that make sense? What should I say about this? This is really undefined. Because you're asking yourself, what power do you have to raise 10 to get 0? Okay. You could answer roughly what? 10 raised to what power would be approximately 0? Yeah, okay, say 10 to the minus infinity. Think of that as being 0. But technically, this is undefined. So if you ask your calculator to do this, you'll get an error message. Okay. Also, if you are asked to calculate the logarithm of a negative number, this would be undefined. Because 10 raised to any power is going to be some positive number. It's never going to be a negative number. Yeah.
Could you maybe say that the limit as b approaches negative infinity of 10 to the b would be 0 and then
Right.
go by the power?
Yeah, you could say, yeah,
Okay.
you could say that. Right. Exactly. Right. Now, there is something called natural logarithms. And these natural logarithms are just logarithms to the base e. So if you have the logarithm to the base e of some number y, you're just asking what power do you raise e to get that value. And oftentimes, they won't use this notation, they'll use this notation. Ln for natural log. So the natural log of y is at whatever power you have to raise e2 to get y. So let me just give you one example. Suppose I ask you to calculate the natural logarithm of 100. Who can tell me what the, using your calculator, what is the natural logarithm of 100? 4.61? Okay. Just carry out to 2 decimal places. So in other words, what does this mean then, Seth? To say the logarithm, the natural logarithm of 100 is 4.61, it means what?
Raise e to the 4.61 in order to get 100.
Exactly. It means e to the 4.61 will be approximately 100 because I think Zach gave me just the answer to 2 decimal places. So if you calculate e to the 4.61, you should get approximately 100. Okay. That's the idea of natural logarithms. And again, natural logarithms are very popular. And one of the reasons they're very popular is because it's easy to get the derivatives. And also, they're the inverse function of the natural exponential function. So that's another reason why they're popular. But talking about derivatives, if you take the derivative of log y with respect to t, no, with respect to t, let's say with respect to y. Excuse me, let me change this notation. The derivative of log t with respect to t, where is the t? What is d log t with respect to t? Do any of you remember this rule?
1 over t.
Just 1 over t. So it's very easy to calculate. 1 over t. There is another formula that you should know. It's a little more general to this one. If you want the derivative of log f of t with respect to t, Ray, do you remember what that formula is? You take the derivative of log f of t with respect to t.
F prime of t over f of t.
Yeah, it's just f prime of t over f of t. It really is the interpretation of a growth rate. Because here's the derivative divided by the value of f. So it's really the growth rate of f with respect to d log f of t. Okay, so you should be aware of those two formulas. They're very simple formulas, and it makes it attractive to use a natural logarithms. There are 3 rules involving logarithms that you should all be familiar with. And I will express these rules in natural logs, although they are true for other bases too. But I'll just write in terms of natural logs. The rule number 1 is this. If you take the natural log of a product, u times v, This is equal to the natural log of u plus the natural log of v. This, I'm not gonna prove this, the book has proofs, but this really follows from the idea that these logarithms are exponents. So, so if you take x to the a times x to the b, that's x to the a plus b. That's where it comes from. Rule number 2. The natural log of u divided by v is equal to the natural log of u minus the natural log of v. So the natural log of a ratio is the logarithm of the numerator minus the logarithm of the denominator. And finally, rule number 3. Chang has about six or seven of these rules, but I'm going to be kind to you. These are the 3 most important ones. You take the natural log of u raised to the a power, that is just equal to a times the natural log of u. And you could just bring that exponent down and multiply times the log. Let me give you an economic illustration of this. You are familiar with this Cobb-Douglas production function? Q equals K to the A power times L to the B power. We could add a constant there if we wanted to, but let me just assume that that coefficient is 1. Okay, to make this clear. Then what happens if we take the natural log of both sides? Well, as long as we take the natural log of both sides, then quality will be maintained, obviously. So we get the log of q equals the logarithm, and then I'll put in brackets, k to the a, l to the b. Now, using rule number 1, you could rewrite this as what? We use rule number 1.
K raised to the a plus L and L raised.
Exactly. This is a product. You have k raised to the a power times l raised to the b power. So you could write this as the natural log of k raised to the a power plus the natural log of l raised to the b power. Then, if you use rule number 3, you could just bring down this a and write this as a times the natural log of k plus b times the natural log of l. And then you see this function, which is very nonlinear to begin with, is now written in a linear form, where your dependent variable is log q. Your independent variables are log k